All right, so we're going to finish off this section by talking about Simpson's rule. Simpson is the name of the mathematician who formally wrote this down as a quadrature formula. And so this approximation, which is the most complicated one that we'll see in this course, is motivated by improving the trapezoidal rule by replacing straight line segments. So under the trapezoidal rule, we would approximate the function itself using straight line segments like this. And then calculating the area. But we can do better. So here, instead of calculating area under the curve using these straight lines, we're actually, for each subinterval, we're going to replace it with a quadratic curve, so a parabola. So we're going to uniquely determine parabolas using 3 points, which means we can really only set this method up if we have an even number of subdivisions. But here's what that would end up looking like. We would take 3 consecutive function value points and use those to construct a parabola. So this one will look like this. And then with the next 3 points, we can set up a separate parabola like this. So let's actually get into the approximation. Of course, the hope here is that if we take a higher order polynomial to approximate the function itself, then the area should also be a better approximation. So we're going to fix the number of subdivisions, an even number of them, and for each consecutive pair of intervals, so we're not just using one interval at a time, we're using 2. So here's interval 1, here's interval 2, 3, and 4, right? Then we're going to take the points x sub I minus 1, f of x sub I minus 1, that's this point, x sub I, f of x sub I, that's this point, and x sub I plus 1, f of x sub I plus 1, and that's the last point on the curve that we're using, and we're going to determine the unique parabola passing through those points. So once we do that, we calculate the area underneath it. So what it would look like is for each subinterval, or pair of subintervals, I should say. So the integral from x sub I minus 1 to x sub I plus 1, so over 2 subintervals at a time, the actual area under the curve we would approximate using the integral from x sub I to x sub I plus 1 of this parabola, the a sub I x squared plus b sub I x plus c sub I dx. This is that parabola we're talking about. And the actual task of finding these values, a sub I, b sub I, c sub I, is laborious, tedious, very detail heavy. Rather than waste your time by going through the whole derivation, there is just a very cool observation that a pattern emerges by sheer nature of the fact that we've picked equally spaced apart values of x sub i's, and we get if we add them all up, the Simpson's rule approximation, S sub n, is delta x divided by 3 times f of a plus 4 times f of x sub 1 plus 2 times f of x sub 2 plus 4 times f of x sub 3 plus 2 times f of x sub 4 plus dot 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 plus 4 times f of x sub n minus 1 plus f of b. So the important pattern here is it goes 1, 4, 2, 4, 2, 4, 1. Okay, it always goes, it starts with a 1, the next one's a 4, the next one's a 2, and then it alternates between 2 and 4 until the second to last one is always a 4 and the last one's a 1. Okay, that's the pattern. Again, the derivation of all that, super not going to get into it because it's complicated. We could do it together, but it's just not worth our time. So, how is this better? Well, our error bound. So the formula now that determines how good this approximates the actual integral says that given the fourth derivative of x is bounded by k for all x values in that interval, the error using the Simpson's rule approximation as a function of the number of subintervals that we pick is no greater than k times b minus a to the 5th power all over 180 n to the 4th power. So wow, that's a lot, right? This means this is on the order of n to the 4th. The error grows as quickly as, or as smaller as, n to the 4th. So as an iterative process, and as a function of n, Simpson's rule converges much faster than the other methods. This is like the golden standard if we're using these kinds of methods. And computationally, not that much more complex than the other ones that we've used. The only difference is, the alternating pattern. You have to remember how to use that or program something to calculate that quickly for you. Okay. So we're going to do an example here. That's kind of an application-based example. Okay. So our application comes from classical physics. Oh, I misspelled it already. Here we go. Classical mechanics. And here what we're working with is we're assuming that we have some pendulum. That's swinging from a hinge point. Here's the vertical axis. So it makes an initial angle, theta naught, with the vertical. And then it swings back and forth. We suppose that it has a length L. Okay? So a pendulum, it'll swing back and forth until it runs out of energy. So the period of this pendulum with a wide angle, so the period is how long it takes to come back to its original position, is given by t equals 4 times the square root of L divided by g, g being the unsigned acceleration due to gravity, times the integral from 0 to pi over 2 of dx over 1 minus sine of 1/2 theta naught squared times sine squared of x. So this integral that we have here, we have no current methods to solve this for us. So we resort to an approximation here. So for simplicity's sake here, we're going to let L be 1 meter. So the pendulum is 1 meter long. G is 9.8 meters per second. And theta naught, the one that we're going to use is going to be pi over 4. Okay, so we're going to assume that we pull it up to a pi over 4 angle with the vertical, and then we let it go, and then we measure the period of the oscillation, how, the movement back and forth. So our task then, we seek to approximate t using Simpson's rule. Okay, specifically, we're gonna take n equals 10. I set this up in a spreadsheet calculator. I just opened up a blank Google Sheets and did the calculations in there. So as you're working with this, you'll see that my table here, I'm taking some specific values of x sub I, because then, given I've chosen n equals 10, our delta x being pi over 20, so pi over 2 minus 0 divided by 10 is pi over 20, is approximately 0.1570710. We're going to do everything in radians, obviously, because we don't care about degrees. Okay, so my values, 0, 0.1571, 0.3141, 0.4712, 6282, sorry. I'm just adding delta x to the previous one each time. 0.7854, 0.9424, 1.099, and there's two more. 1.2566 and 1.4136. Okay, those are my x values. My f of x sub I values. Assuming I'm using, in this case, f of x is the integrand, right? So 1 over 1 minus 0.146447 sine squared of x. Where did I get that 0.146447? So I took this and I plugged in pi over 4 and squared it. Okay? And I approximated because we're using a calculator, so we're doing that anyway. So there might be some round off error here. You'll have to be careful about that. That's not something that we're going to focus too much on here because it's beyond our scope. But in a proper numerical analysis class, that is kind of something that we would have to worry about. So the first function value is 1, and then 1.0036, 1.0142, 1.0311, 1.0533, 1.0790, 1.1060, 1.1315, 1.1527, 1.6667. Okay, those are my function values, which means in order to find, so the actual S sub 10 that I'm going to perform, right? So remember, S sub 10 is delta x divided by 3 times the first function value times plus f times the second function value plus 2 times the second, and so on, right? All the way until you get down to the last one. So just keep track of, what you need to multiply each one by. So 1, 4, 2, 4, 2, 4, 2, 4, 2, 1. And if you're following along by using a spreadsheet, just go ahead and put those in the next to each other in a different column. And then you can use a function. If you're using Google Sheets, there's a function called sum product, which is basically going to take your two columns, multiply each entry together. So it'll actually perform these multiplications and then add all those things together. And that's exactly what we want. So you can do that. You can set it up that way in Google Sheets and Excel. It doesn't matter. Okay, all said and done. I'm going to skip the painful work here. Our actual approximation is going to be 4 times square root of 1 over 9.8. And this should give us the proper units of seconds. Times s sub 10, which is what we should get after calculating all this, right? So delta x being the 0.1570710 divided by 3 times all this calculation that we do using sum product. And that we estimate is approximately 1.8598 seconds. And that's it. So Simpson's rule, very powerful result. Not much more complicated than the other ones that we found, but it's a vast improvement. And all we had to do was multiply the function values by some interesting combination of integers. So if you're interested more in that, feel free to, ask me. I'm more than happy to talk your ear off about this sort of thing. But what you should know moving forward with, now you've concluded this section, you are going to be expected to actually perform the approximation. So given a function and an interval, approximate using the given rule. So midpoint, trapezoidal, Simpson's rule. And for each one, find the error if there is the exact value that's being given to you. Or find an error bound. Okay. For Simpson's rule, that's going to be like really, you'd have to find the fourth derivative of f, and that's